Okay, satellite of mass m orbits a planet of mass m. So I have here a satellite and another. So this is a planet and this is a satellite that move at a distance of r. Rotates around at a distance of r from the center of the planet. What's the work that must be done? So the satellite can increase its orbital to the orbital. So now the satellite, I need to put it at a further distance, which is 2r. What is the work needed to that job? So first, work equal to the change of energy. So this question could be a little bit tricky because the topic 10 equation in the data booklet are more concentrated on the potential energy. And in this example, you will miss that there is a change also in the kinetic energy. So here we need to find the total energy instead of only the energy, because I have potential energy and kinetic energy. Both are going to increase or to be changed to allow the satellite to move at a further orbit, because we know that each orbit had a different velocity. So we have here different velocities for the rotation. So the first step here, I need to find a formula for the total energy, because this problem is about proving the correct formula. So first, I need to find the total energy formula. Just work with the formula without any numbers or any other concept. The total energy here is the potential energy of satellites plus the kinetic energy. Potential energy from the equations from topic 10 is negative G mm over R. Why we didn't use the mgh equation from the mechanics? Because this is topic 10 equations, and we have the choices as m over R. Plus the kinetic energy, which is half mv squared. This is one from the mechanics, because we don't have a kinetic energy equation straightforward in the data booklet for topic 10. So here the orbital velocity. Orbital velocity is, so let's do it as negative G mm over R plus half m. The orbital velocity is root G mass of planet over R all to the power 2, because the equation actually has power 2. And here the power 2 will cancel the root, leaving Gm over R isolated without a root. Then we can put the equation in a simpler form. G mm over R plus half m multiplies the bracket will be G mm at the numerator and 2R at the denominator. Okay, to solve this formula, we multiply both terms by 2 for the potential energy equation to have a common denominator, which is 2R, and then have negative 2 GMM plus GMM that will give us negative GM m over 2R. So imagine you have this one as negative 2 GMM and this one as GMM plus GMM, and we add them together, we'll get negative GMM over 2R. So this is the formula for the total energy. What will be the formula for the work? Total energy subtract each other from the second position and the first position. I'm going to clear this slide to make it clear to work the rest of the solution. Okay, so we know that the first position R1 is R, the second position R2 is 2R. And we just had proven that the total energy is negative G mass of planet, mass of satellites over 2R. So the work equals the total energy of the second position, the further one, minus the total energy of the first position. So it'll be negative G m over 2 times the R2 is 2R minus Gm m over the first position is just 2R. So we need to subtract this, the total energy of the second position, the one further away, by WR, and the second equation is for the first position. Subtracting both equations from each other, we need to have a common domain. So we're gonna multiply this here by 2 in both terms. We'll get negative g m m over 4r plus negative plus g m m. Don't forget the 2 here, and 2 multiplies to r, so we now have a common denominator. We can find the answer as negative g plus 2g would be positive g mm over 4r. So the answer here will be number C.